செந்தமிழ்ச்செல்வன். செந்தமிழ்ச்செல்வன் கேக்குதுங்களா? கண்ணா கேக்கலையா கண்ணா?
எஸ் மேம்.
கண்ணா எப்படி உங்களுக்கு ப்ரிப்பரேஷன் போயிட்டு இருக்கு?
It's going well, ma'am.
ஓகே. சாமி, இப்போ நம்ம கான்செப்ட்ஸ் எடுத்து கொஸ்டின்ஸ் எடுக்கிறோம் இல்லைங்களா? வெறும் நியூமரிக்கல் மட்டும் டிஸ்கஸ் பண்ணா ஹெல்ப்ஃபுல்லா இருக்குமா? நீங்க என்ன நினைக்கிறீங்க? சப்போர்ட்டிவா இருக்கும்னு நினைக்கிறீங்களா? இல்ல வெறும் ஐ மீன் கான்செப்ட்ஸும் நியூமரிக்கலும் தான் வேணும்னு நினைக்கிறீங்களா? எப்படி கண்ணா வேணும்? ஒப்பீனியன் தான் கேட்கிறேன்.
If you have more numerical, ma'am, it will be more useful, ma'am.
ஓகே. அப்போ 12th ஸ்டாண்டர்டுக்கு நம்ம நியூமரிக்கலுக்குள்ள போயிட்டு நியூமரிக்கல் சால்வ் பண்ண எங்கெங்கெல்லாம் கான்செப்ட் சப்போர்ட் வேணுமோ அப்படி டிஸ்கஸ் பண்ணலாமோ?
Yes, ma'am.
ஓகே. சரி, அப்போ நம்ம அந்த ஈக்லிபிரியம் மட்டும் முடிக்கலாம். ஈக்லிபிரியம் முடிச்சுட்டு அதுக்கப்புறம் நம்ம 12th ஸ்டாண்டர்ட்ல இருந்து ஒரு சாப்டர்னா ஃபர்ஸ்ட் நியூமரிக்கல் ஸ்டார்ட் பண்ணி நியூமரிக்கல் டிஸ்கஸ் பண்ண எங்கெங்கெல்லாம் கான்செப்ட் சப்போர்ட் வேணுமோ அந்த இடத்துல கான்செப்ட் டிஸ்கஸ் பண்ணிட்டு நியூமரிக்கல் போகலாம். சரிங்களா?
Okay, ma'am.
ரைட். போர்டுக்கு ப்ரிப்பரேஷன் எப்படி கண்ணா போகுது?
Fine, ma'am.
ஓகே. ஒரு 2-3 மினிட்ஸ் வெயிட் பண்ணலாம். Good evening, everyone. So, shall we start the session? Right. So, we have been discussing ionic equilibrium, right? So, in last class, we have discussed different pattern of pH related questions that is more specifically of strong acids and strong bases, right? And also, we have discussed also Ostwald's dilution law and ionic product of water. So, today we'll be discussing few more concepts like hydrolysis of salt, buffer solution, common ion effect, sparingly soluble salt or solubility product. Okay. So before getting into new concepts, we'll discuss couple of problems. Then we'll move on to new concepts. Okay. Are you guys comfortable in calculating pH? Are you guys comfortable in calculating pH of any solution given? I'm talking about strong acids and strong bases. Are you guys comfortable with that patterns? Okay, fine. Now the question is the degree of ionization of zero point 0.1 molar bromoacetic acid solution is 0.132. Calculate the pH of the solution and pKa of bromoacetic acid. Kana, in last class, we have discussed pH related problems that is specifically for strong acids and strong bases, in which we have discussed around 8-9 patterns, right? So they'll be giving H plus ion concentration, we'll be calculating pH, or they'll be giving the concentration of acid. From that, we'll be calculating pH, H plus ion concentration, after which we'll be calculating pH, right? So here, the question is about pH, but the system is not a strong acid. Actually, it is a bromoacetic acid. Bromoacetic acid is not a strong acid. It is an organic acid. Usually, organic acids are considered to be a weaker one. So here I have bromoacetic acid. So first we'll write the structure of bromoacetic acid. Okay. Now, obviously, we know the structure of acetic acid. What is the formula of acetic acid? It is CH3 COOH. And here they are talking about bromoacetic acid, which means instead of this hydrogen, one of the hydrogens, we're going to substitute bromine. So the formula is CH2. Instead of one hydrogen, I'm substituting bromine, and I have carboxylic acid group, which is COOH. And upon dissociation, since it is a weak acid, it will get dissociated partially. So the system will be in equilibrium. So CH2, Br, COO minus, and H plus. So this is how bromoacetic acid will get dissociated. And they've given you the concentration of bromoacetic acid, which is C, whose value is 0.1 molarity. And what is this 0.132? What is that 0.132?
Alpha, ma'am.
Yes. So 0.132 is a degree of ionization or degree of dissociation, which is alpha. So since the question is about weak acid, we're going to use Ostwald's dilution law. According to Ostwald's dilution law, we know the derivation and the relationship between alpha, Ka, and C, right? So here, what is the question? We have to calculate pH and also we have to calculate pKa. So initially, when time t is equal to 0, I've taken a C concentration of acid. Before the reaction occurs, the concentration of anion and cation will be 0. But when the system is at equilibrium, a particular quantity of acid would have been dissociated, right? So I'm going to take it as C alpha. If C alpha quantity of if C alpha quantity of bromoacetic acid was dissociated, then what will be the remaining quantity? C minus C alpha. Similarly, the quantity of anion formed will be C alpha and quantity of H plus ion formed will be C alpha. Now, the first question is we have to calculate pH, right? And what is the formula to calculate pH? pH is equal to minus log. Very good. Minus log of H plus ion concentration. Super. So here to calculate pH, we are in need of H plus ion concentration. Here, since the acid is a weak acid, we cannot calculate H plus ion from this concentration of acid. If the acid is a stronger one, then from the concentration of acid itself, we'll be calculating H plus ion concentration. But here, bromoacetic acid is not a strong acid. So this value will not give us the concentration of H plus ion. But we have to calculate H plus ion using C alpha because here the dissociation is a partial dissociation. So when the system is at equilibrium, H plus ion concentration inside the solution will be C alpha. So concentration of H plus ion is nothing but C alpha. So what is C? C is the concentration of acid, which is 0.1. I'm going to have it as 10 power minus 1. And what is alpha? 0.132. That's it. So if you multiply these two numbers, you'll get the value of H plus ion, right? So you'll get the concentration of H plus ion from which we can calculate pH. Could you please calculate H plus ion's concentration and from which please calculate pH of the solution? Calculate pH of the solution. How we can do that, Kana? See, it is 0.132 into 10 power minus 1, right? I'm going to have it as 1.32 into 10 power minus 2. That's it. So this is H plus ion concentration from which we can calculate pH. So pH is equal to minus log of H plus ion concentration is 1.32 into 10 power minus 2. So it is like log A into B. Please apply that formula, multiply this negative sign inside and simplify and come up with the value of pH. So 2 minus log 1.3, right? If you guys want me to solve, then let me know, I'll do it. Okay, Muthulakshmi is getting 2. Okay. Okay, I'll solve here. Guys, listen. pH is equal to minus log of 1.32 into 10 power minus 2, right? So I'm going to have this minus sign outside. It is like log A into B. This can be written as log A plus log B, right? So minus of log 1.32. It is like log A power B, which can be written as B log A. I'm going to bring this power to the front. So minus 2 log 10. What is the value of log 10? It is 1. So minus of 0.32 minus 2. What is the value of log 10? It is 1. So 2 into 1 is 2. That's it. I'm going to multiply this negative sign inside. That is 2 minus log 1.32. And now listen here. Here the value is 2 minus log 1.32. So what it means? From 2, you're going to subtract some value, right, Kanna? So definitely pH will be less than 2 and definitely not 2. You're getting my point, Putlakshmi?
Yes, ma'am. Yes, ma'am.
Value will not be 2. So definitely answer will be less than 2. According to our option, see, here we have two options which got pH less than 2, which is option A and option B, option C. Definitely answer will not be B and D. Right, Kanna? Because the value will be less than 2. Here it is 2 minus log 1.32. We can assume a value for log 1.32 to get the exact value, right, Kanna? Because log 1 will be 0 and log 2 will be 0.3010. So log 1.32 is somewhere between 0 and 0.3. You can assume a value between 0.3 and 0. So could you please come up with any value between 0 and 0.3? Any approximate value will do. Log 1.32's value. Value must be between 0 and 0.3. Any value kanna between 0 and 0.3. Why? What happened? Any value between 0 and 0.3. Okay, Muthulakshmi's answer is 0.2. Fine. So here I'm going to take it as 0.2. So 2 minus 0.2 is 2 minus 0.2 is 1.8. Right, Kana? That's it. So pH of the solution is 1.8. That's it. We got pH of the solution. So the next question is we have to calculate pKa, and definitely answer will not be second and fourth option. Now we're going to calculate pKa. To calculate pKa, we are in need of Ka value, right? And what is the formula to calculate Ka? We have alpha, we have C. So the formula according to Ostwald's dilution laws, alpha is equal to root of Ka. So what is Ka? Alpha square C, which is equal to Ka. You have the value of alpha, you have the concentration. If you simplify that, you'll get the value of Ka. From Ka, we can calculate pKa. What is the formula? pKa is equal to minus log of Ka. That's it. So is it possible for you guys to solve the rest of the problem? Can you please do this as activity? Fine. Okay, Kanna. So first job is you have to calculate Ka from the values of alpha and C, and from Ka you have to calculate pKa. And formula to calculate pKa is minus log of Ka. That's it. Now we'll move on to next question. Do rest of the problem is activity, okay? Fine. So the next question is the ionization constant of HF, HCOOH, HCl at 298 Kelvin are 6.8 into 10 power minus 4, 1.8 into 10 power minus 4 and 4.8 into 10 power minus 9 respectively. Calculate the ionization constant of corresponding conjugate base. See, what are all the chemical species they have given us? One is HF, another one is HCOOH, and third one is HCN. And for these systems, they've given you the ionization constant, which is 6.8 into 10 power minus 4, 1.8 into 10 power minus 4, and 4.8 into 10 power minus 9. And they're asking us to calculate the ionization constant of their conjugate base. Kana, for HF, what will be the conjugate base? HF is an acid, right? So if HF is an acid, what will be the conjugate base of HF?
F minus, ma'am.
Very good, it is F minus. So F minus is the conjugate base of HF. And for this, we have to calculate ionization constant. For acids, the ionization constant is ionization constant can be represented by Ka. For conjugate base, ionization constant can be represented by Kb. That's it. So they've given you the value of Ka and they're asking us to calculate Kb. What is the relationship we have discussed in last class? Kw is equal to Ka into Kb. Could you please tell me the value of Kw? At 298 Kelvin, the value of Kw is a constant, and we know the value also. Come again, Kana? Yes, Sindhamichelvan? Okay, it is not 14. pKw is 14. But here I'm asking for Kw. pKw is 14.
10 power minus 14.
Yes, it is 10 power minus 14. Kw value is 10 power minus 14. pKw is 14. So here we have Ka value and we know the value of Kw from which we can calculate Kb. Okay. And similarly for HCOOH, for formic acid, what will be the conjugate base? HCOO minus. And for HCN, the conjugate base will be CN minus. So from the values of Ka and Kw, we have to calculate Kb. That's it. Is it possible for you guys to do it? Can you do it as activity? Right. So, as far as ionic equilibrium is concerned, we have discussed what is electrolyte, different types of electrolyte. We have discussed what is degree of dissociation. We have discussed what is acid base, different concepts for, different definitions for acids and bases, like Arrhenius concept, Bronsted, Laurie, Lewis concept. After which we have discussed all the different pattern of pH related problems for strong acids and strong bases. After which we have discussed Ostwald's dilution law and ionic product of water. Now we're going to discuss solubility product of sparingly soluble salt. Kana, what is sparingly soluble salt? What is mean by sparingly soluble salt? What is mean by sparingly soluble salt? Okay, not fully dissociated. Yes, kind of. You're partially right, Mutlakshmi. Okay, we'll see. Kana, listen here. I'm going to take a hypothetical salt, which is AB. Okay, and I'm for this AB salt, the solubility is 10 gram. What is mean by solubility? For example, I have a beaker of water, say 100 ml. Okay, I have 100 ml of water. In this 100 ml of water, maximum of 10 gram can be dissolved. So the solubility of the salt is just 10 gram. So solubility is nothing but the maximum quantity of salt that can get dissolved in a particular quantity of solvent. That is solubility. Okay, so solubility is the maximum quantity of salt that can get dissolved inside a particular quantity of solvent. That is the solubility of salt. So I have a salt called AB. This is a hypothetical salt for which I've given you the hypothetical solubility as 10 gram. Maximum of 10 gram can get dissolved. More than 10, it cannot dissolve. Okay. See, this is the solubility. For example, I have a salt called XY, whose solubility is 15 gram. Could you please tell me among AB and XY which got more solubility? Which got more solubility? Among AB and XY, which got more solubility? Yes, XY got more solubility. This can get dissolved of 15 grams. I have a salt of PQ, and solubility of salt is 0.0005 gram. So among AB, XY and PQ got the lowest solubility. Only 0.0005 gram of salt can get dissolved inside this particular quantity of solvent. So this is called as sparingly soluble salt. Salt whose solubility is very much less than that kind of salt is called sparingly soluble salt. You getting my point? Right. Now we are talking about the salt called AB. Now we're going to discuss what is saturated, what is unsaturated, and what is supersaturated solution. I think we have discussed this already. Right. We have discussed about saturated, unsaturated solution.
Yes, ma'am.
Okay. So what is unsaturated solution? For example, the salt AB can get dissolved of around 10 gram inside the solution, right? I'm going to dissolve a 6 gram of the salt. Will it get dissolved inside the solution? Maximum quantity can get dissolved is 10 gram. Now I'm going to dissolve just 6 gram inside the solvent. Will it get dissolved? Definitely, right? Maximum 10 gram it can dissolve. Now I'm just adding only 6 gram. It will get dissolved, right? Again to the solution, I'm going to add 2 more gram of the two more gram of salt. Will it get dissolved? it will get dissolved, right? 10 gram, maximum 10 gram can be dissolved. Now I've added only 8 grams. Now again, I'm going to add 2 more gram. Definitely it will get dissolved. Now I'm going to add another 1 gram. Will it get dissolved, Kana? Okay, not under same condition. I'm not changing the condition at all, Sandamil children. At same condition, I'm going to keep on adding the salt. That's it. I'm not changing the temperature and all. So after 10 gram, it will not get dissolved, right? So till this stage, the solution is called unsaturated solution. Because till this stage, I've added only the quantity of salt which is less than the original solubility of the salt. Exactly at this point, I've added exact solubility of the salt, and after which it will not get dissolved. So this particular stage is called saturated solution. After that, that is called supersaturated solution. So whenever the solution is considered to be unsaturated solution, AB will get completely dissolved into A plus and B minus. So this is undissociated salt, but it will get dissociated into A plus and B minus. That's it. But whenever the solution is said to be a saturated, then at that time a equilibrium will be established between undissociated salt and its dissociated ions. Whenever the system attains a saturation, then the system will attain an equilibrium between AB, that is undissociated salt, and its dissociated ions. So here for AB, that saturated point will be at 10 gram, right? For XY, the saturated point will be at 15 gram. But for PQ, when the saturated point will be attained, just by adding 0.005 gram of salt. You're getting my point? Because the solubility of PQ is very much less. So if you add just 0.0005 gram of that particular salt in a solvent, equilibrium will be attained. You're getting my point, Kana? So whenever you're discussing about a sparingly soluble salt, they'll give you a proper equilibrium reaction. Okay. Now we're going to talk about a proper sparingly soluble salt. So sparingly soluble salt is nothing but salt whose solubility is very much less. I'm going to take a hypothetical salt of formula AXBY. This is a salt. Generally, any salt will be having a cation and anion. Here also we have A cation and B anion with particular number of cations and with particular number of anions, right? When the system is at saturation or when the system is at equilibrium, how this, what will be its constituent ions? How it will get dissociated, Kanna? If you dissolve a sparingly soluble salt, definitely a very small quantity would have get dissociated, right? What will be the dissociated ion? Whenever we are writing the ions produced, see, one will be having a cation and anion. A and B were separated. How many A was there? X times of A and Y times of B. The first species will get a positive charge and second species will get a negative charge. How many positive charges we'll be having? How many number of B we have? Y. So Y times of positive charge. And how many negative charge we'll be having? How many number of A we have? X. So X times of negative charge. That's it. That's it. Fine. So this is how the sparingly soluble salt will get dissociated. Fine. Now the system is an equilibrium. Here this is the undissociated salt which is in solid state and they were their constituent ions which is present inside the aqueous solution. So it will be AQ. That's it. Whenever the system is in equilibrium, we'll be writing an equilibrium constant, right? Could you please tell me the expression for equilibrium constant? Capital K is equal to, what is the expression, Kanna? Concentration of product divided by reactant. What are all the products we have here? What are all the products we have here? A and B. So concentration of A, number of moles we'll be writing on the power, right? And concentration of B power Y divided by concentration of AXBY. Now, what is the physical state of AXBY? It is in solid state. For any solid, for any liquid, concentration will be unity.
One
We have
by.
discussed in chemical equilibrium. Yes, Muthulakshmi, it is 1. So it is a constant. This is also a constant. We're going to multiply these two constants. Whenever we are multiplying two constants, we'll end up with another new constant. Here, the new constant, I'm going to represent it as KSP. KSP, which is equal to A power X and B power Y. That's it. See, we have a new term for KSP. See, KSP is nothing but an equilibrium constant. But here, this will have a new name called solubility product. So, KSP is nothing but solubility product. In most of the cases, we have seen equilibrium constant, but based on the concept, we are giving the name for that equilibrium constant. See, we have seen Ka, Kb, Kw and all that. All were equilibrium constants, but based on the concept, we gave name as acid dissociation constant, base dissociation constant, ionic product of water, right? Similarly, Ksp is also an equilibrium constant, but here we are giving a term called solubility product. That's it. Now, this is one of the formulas which relates solubility product and their concentration of ions. And also, I'm going to expand this formula. Listen here. I have a salt called aluminum chloride. Okay. How this aluminum chloride will get dissociated? Aluminium and chlorine. How many aluminium we have? Left side we have only one aluminium. So 1 aluminium, and we have 3 chlorides. So 3 times of Cl. First species will have positive charge and second species will have negative charge. How many positive charge we have to write? How many chlorides I have? 3. So 3 positive charges. And how many negative charges I have to write? I have only 1 aluminium, so only 1 negative charge. So this is how aluminum chloride will get dissociated. For example, now I have only 1 aluminum chloride and that aluminum chloride was dissociated. So from 1 aluminum chloride, how many aluminum 3 plus and how many Cl minus we'll be getting? If 1 aluminum chloride was dissolved inside the solution, how many aluminum 3 plus and Cl minus will be obtaining? From 1 aluminum chloride, we'll be getting only 1 aluminum 3 plus and we'll be getting 3 Cl minus, right? So 1 Al 3 plus and 3 Cl minus. You guys getting my point? Okay. For example, I have 10 aluminum chloride dissolved inside the solution. How many number of aluminum 3 plus and Cl minus will be obtaining?
10 aluminum and 30 chloride, ma'am.
Very good, Kana. So 1 into 10 aluminum 3 plus and 3 into 10 Cl minus. Very good. For example, I have 0.1 molar aluminum chloride were dissociated or dissolved inside the solution. So quantity of aluminum 3 plus will be 1 into 0.1 and 3 into 0.1. Right, Kana? Similarly, I have C concentration of aluminum 3 plus were dissociated. So quantity of aluminum 3 plus will be 1 into C and Cl minus will be 3 into C. That's it. So similarly, here I have a salt called AXBY. In this salt, the quantity dissolved inside the solution will be yes. Already it is a sparingly soluble salt. So the solubility will be very much less. That is considered to be yes. So yes, quantity of salt was dissolved inside the solution. And I want you guys to tell me the quantity of cation and anion obtained in the solution. If S quantity of sparingly soluble salt dissolved inside the solution, then what will be the quantity of cation and anion formed? Yes, X times of yes and Y times of Y. That's it. Mutlakshmi is perfect. That's it. Right, Kana. Now we're going to substitute the concentrations of cations and anions in this equation. Okay. As I've told you already, I'm going to expand this equation. KSP, which is equal to concentration of A Y plus is X times of S power X, and concentration of Bx minus is Y times of S power Y. So KSP is equal to X times of X, S power X, Y times of Y, S power Y. So therefore KSP is equal to X times of X, Y times of Y. And for these two terms, we have a common base, which is S, and powers are added as X plus Y. So this is another equation. Is also a very important one. So here KSP is the solubility product and S is the solubility of that salt. Solubility of the salt or the concentration of the salt which was dissolved. Okay, that's it. So they may give you any salt and they may ask you to write the relationship between KSP and S, or they may ask you to calculate the solubility of the salt by giving KSP, or they may ask you to calculate KSP and they'll give you the solubility of the salt. So they may give you any term among KSP and S, they may give you any of the terms and they may ask you another parameter to calculate. That's it. So we'll do one problem related to that. I have a salt called lead chloride, PbCl2. Could you please tell me how this lead chloride will get dissociated? How PbCl2 will get dissociated?
Pb plus 2 plus Cl2 minus. Cl minus.
Okay, Pb2 plus
2 Cl minus.
Very good, Kana. 2 times of Cl minus. That's it. Now we're going to write the relationship between KSP and S for this particular salt. So what is the formula? KSP is equal to X power X, Y power Y, S power X plus Y. Right. So KSP is equal to, here what is X? Basically what is X? The coefficient or the number of moles of cation is X and number of moles of anion is Y. So here the cation is Pb2 plus and the number of mole is 1. So here this is X and this is Y. So 1 power 1 and 2 power 2, S power 1 plus 2. That's it. So KSP is equal to 2 power 2 is 4. S power 1 plus 2 is 3. That's it. This is the relationship between KSP and S for this sparingly soluble salt. That's it. So for example, if KSP is given, please substitute the value of KSP here. If suppose value of KSP is given as C. So how you will do it? C by 4, which is equal to S cube. If KSP is C. So how you will calculate the value of S? See, to take square root, it is easy. Now we're going to take cube root. If the power of S is more than 2, then the numerical is getting complicated, right? So to do that, please use log values. Please use log concept to simplify the problem, okay? I'll give you a problem. I'll give you a problem related to this so that we'll solve it. Okay, please note it down. I'll give you a problem, Kana. In that problem itself, I'll teach you how to solve that log values also. Okay, shall we discuss a numerical? Fine. See, the question is the solubility product constant of Ag2CrO4 silver chromate and AgBr silver bromide are 1.1 into 10 power minus 12 and 5 into 10 power minus 13 respectively. Calculate the ratio of the molarities of their saturated solutions. See, here the question is, first, you have to calculate the molarities of each system. What is molarities? What they mean? Here, they are talking about concentration or the solubility of each salt. So first you have to calculate the solubility of silver chromate and you have to calculate the solubility of AgBr. Solubility is, solubility, they mentioned it as molarity. That's it. So after finding the solubility of each salt, you have to find the ratio between them. That's it. So the first salt they are talking about is Ag2CrO4, silver chromate. So since they are talking about solubility product, obviously it is a sparingly soluble salt. So it will get dissociated partially into, how it will get dissociated, Kanna? How it will get dissociated? How the silver chromate will get dissociated?
2 Ag plus CrO4 2 minus, ma'am.
That's it. Yes. So this is salt and they were dissolved in water. So it is an aqueous medium. That's it. So we have to calculate solubility, right? And we have a direct formula. Ksp is equal to x power x, y power y and s power x plus y. So here Ksp of silver chromate is 1.1 into 10 power minus 12, which is equal to, here x is 2, so 2 power 2 and y is 1 power 1, s power 1 plus 2 is 3, right? So this is 1.1 into 10 power minus 12 divided by 4, which is equal to s cube, right, Kanna? Can you please solve this? What we'll be having in have it in the left side. So do it as 11 into 10 power minus 13 divided by 4. What is 11 by 4? What is 11 by 4? What is 11 by 4? Yes, 2.7. Listen here. S cube is equal to 2.7 into 10 power minus 13. Now we have to find the value of S. We have to take cube root. It will be little tricky. So to solve this, what I'm going to do is take log on both sides. Log S cube is equal to log 2.7 into 10 power minus 13. Left side it is like log a power b, which can be written as b log a, which is equal to, it is like log a into b, which can be written as log a plus log b. That's it. So 3 times of log s is equal to, what is the value of log 2.7? We know the value of log 2 is 0.3010 and log 3 is 0.4771. Now I'm asking the value of log 2.7 somewhere between log 2 and log 3, which means the value is between 0.3 and 0.4771. Could you please tell me any approximate value Kana between 0.3 and 0.4771?
0.37, ma'am.
Okay, 0.37 is right. I'm just taking the approximate value. So it is log 10 power minus 13, which can be written as minus 13 log 10. Right, that's it. So please simplify this. 13 minus 0.37, which is minus minus 12 point, how much Kana? 12.63, right? So minus 12.63 divided by, I'm just bringing 3 to the right side. So in denominator, we have 3. So if you simplify this, what we'll get it in the right side? 12.63 divided by 3.
4.21, ma'am.
Very good. It is 4.21. So log S is equal to 4.21. So what is S? Antilog of 4.21 minus, right? So please simplify this. We now have to take antilog, right, Kana? Can you please solve this? Take antilog for minus 4.21.
(1.61 into 10 power minus 4, ma'am.
Okay. Come again, Kana. What is your answer?
1.61 into 10 power minus 4.
Okay. Can you please check this once again?
Okay, ma'am.
How about rest of the students? Mushkan, Bhumika, Senthimil Chilvan. Shall we do it together? How we have to take antilog for this number? We have to separate these values before decimal point and after decimal point. So before decimal point is 4, so minus 4 minus 0.21. Whenever we have a negative sign before this decimal number, what we have to do? We have to add minus 1 and plus 1. So minus 1 plus 1. So minus 4 minus 1. So which is minus 5 plus 1 minus 0.21. Simplify that. My 1 minus 0.21, which is 0. Plus 0.79. Right, Kana? So antilog of minus 5, we have to write it in terms of log, which can be written as log 10 power minus 5. Similarly, we have to write 0.79 in terms of log. How we can do that? log 7 is 0.8450, right? Log 5 is 0.6989. We are in need of 0.79. So values between log 5 and log 7. Even you can calculate the exact value of log 6 also. You can simplify the value for log 6, right? Okay, it is not necessary. You just guess between log 5 and log 7. Anything is fine, Kanna. I want to write 0.79 in terms of log. That's it. If possible, can you please calculate the value of log 6? What is the value of log 6? We haven't memorized that, right? Have to write this log 6 as 2 into 3. So you have to write it as log 2 plus log 3. We know the value of log 2 and 3. Please add those values and tell me the value. So log 6 will be 0.77. Right, Kana? So log 6 will be 0.77. So we have to write the value of, we have to write 0.79 in terms of log. So approximately, definitely it will be more than 6, right? Shall we have it as 6.1? So I'm going to write 0.79 in terms of log as log 0.6. Log 6.1. That's it. So it is like log A plus log B. I can write it as log A into B or B into A. That's it. So if you cancel anti-log and log, S will be 6.1 into 10 power minus 5. This is the answer. This is the solubility of silver chromate. So we are done with the first part of the problem. Second is you have to find the solubility of AgBr. That is quite easy. Can you please do it, Kana? We know how this AgBr will get dissociated. You know the value of X and Y, and we know the relationship between KSP and S. We have the formula, substitute in that formula and calculate the value of S. Solubility of AgBr is given as 5 into 10 power minus 13. Please do it at your end. Taking square root is very easy. You don't want to take log also. You can take directly square root of the values and you can find the solubility. If you're finding it difficult, please let me know. We'll do it together. If you guys want any clue or any support, please let me know. We'll do it. Yes, Kanna?
I guess 7.1 into 10 power minus 7, ma'am.
Very good. 7.1 into 10 power
10
minus
power minus 7.
Very good, Mutlakshmi. How about rest of the students? If you're getting different value, please let me know. Or if you don't know how to do it also, please let me know. We'll do it now. Sendamil Chelvan, what answer you got? Mushkan? Okay. Anyways, I'll do it here. Listen. AGBR and Muthulakshmi's answer is right. Kana, what is the value? Kana 7.1 into 10 power minus
7, ma'am.
7. Right. Okay. We'll check here. AGBR. We know it will get dissociated partially into AG plus and BR minus. So KSP is x power x, y power y, and s power x plus y. KSP is given as 5 into 10 power minus 13. Here value of x is 1, 1 power 1, value of y is 1, 1 power 1, s power 1 plus 1, which is 2. So 5 into 10 power minus 13, which is equal to s square. So we have to take square root. So how to take square root? See, whenever you're taking a square root, please make sure the power of 10 is even number. Here it is odd number. We can make it even. How to do that? Shall I write it as 15 to 10 power minus 14? That's it. So if you take square root 50 into 10 power minus 14, which is equal to s square. So root 50 into root 10 power minus 14, which can be written as power 1 by 2. So we can cancel these numbers. 14 by 2 is minus 7. So root 50 into 10 power minus 7, which is equal to s. So what is root 50? We know root 49 as 7. So it's a 7 point something, right? So Muthulakshmi took it as 7.1. That's it. Which is right. So we have the solubility of Ag2CrO4 and AgBr. They're asking us to find the ratio. So solubility of Ag2CrO4 divided by solubility of AgBr. So here it is 6.1 into 10 power minus 5 and this is 7.1 into 10 power minus 7. Take it as 6, take it as 7, no issue, 6 by 7. So 6 into 10 power minus 5. I'm bringing this 10 power minus 7 to the numerator. So it is 10 power plus 7 divided by 7. So please simplify this, Kanna. What is 6 by 7? What is 6 by 7? 0 point? Yes, 600 by 7. You're right, Muthulakshmi. I want to simplify that. Your answer is right. 600 by 7 is right. Six hundred by 7. Kanna, 600 by 7. Kanna. So it is 85.7, right, Muthulakshmi? It's not 8.57, it is 85.7. So this is the answer. So solubility of Ag2CrO4 divided by solubility of AgBr, which is equal to approximately 86, right? That's it. So could you please tell me which got more solubility than? Solubility of Ag2CrO4 is 86 times the solubility of AgBr. That's it. That's it, Kanna. Fine. Now, shall we move on to next concept? Okay. So we are done with solubility product. Now we'll move on to hydrolysis of salt. Hydrolysis of salt. What is mean by lysis? We are breaking something. We are breaking some molecule. Here it is hydrolysis, which means we are using water molecule to break. We are using water to break a particular compound. The compound what we are talking is salt. So we're going to break the salt using water molecule. That's it. So let us take a salt, a very famous one, which is NaCl. I'm going to use water to break this molecule. Basically, I'm adding salt into water. How this NaCl will get dissociated? Na plus and Cl minus. How water molecule will get dissociated? H plus and OH minus. So here Na plus will combine with OH minus to give NaOH. And H plus and Cl minus will combine together to get HCl. That's it. So if you dissolve any salt in water, we'll end up with a base and acid. Here, as far as sodium hydroxide is concerned, we have strong base. As far as HCl is concerned, it is a strong acid. Based on the nature of the salt you are dissolving, you'll end up with different strength of acid and base. Here we got strong acid and strong base, but in some case we'll be getting both the systems are weak, or strong base, weak acid, or weak base, strong acid. We have 4 possibilities there. Okay. But as far as sodium chloride is concerned, if you dissolve sodium chloride in water, we'll end up with strong base and strong acid. Here, in the solution, see, I have a beaker full of water in which you have dissolved sodium chloride salt. So here we got sodium hydroxide, which is a strong base, and HCl as strong acid. Here, both the system got same strength. Here, no one is dominating. So the system will be neutral. And pH of the solution will be 7. Right, Kana? But I have another salt here, which is CH3COONa, which is called sodium acetate. I'm going to dissolve the sodium acetate in water. Could you please tell me what are all the acids and bases we'll be getting here? What acid and what base we'll be obtaining here? How sodium acetate will get dissociated? CH3COO minus and Na plus. And how H2O will get dissociated? H plus and OH minus. So CH3COO minus will combine with H plus to get CH3COOH and NaOH. This is a strong base. Acetic acid is an organic acid. Obviously, it is a weak acid. Now tell me which is dominating. Is it acid or base? Which is dominating? Which got more strength? Base, right? So in this solution, base is dominating. Now tell me what will be the nature of the solution. Will it be acidic or basic?
Basic.
Very good. So now the solution will be basic and pH will be definitely greater than 7. Okay. That's it. So here in this hydrolysis of salt, we have 4 combinations: strong acid, strong base, weak acid, strong base, strong acid, weak base, and weak acid, weak base. Okay. Now I'm going to give you all the formulas related to these combinations, and derivations are not necessary. So I'll give you just the formulas and we're going to use that formulas to crack the numericals related to hydrolysis of salt. Okay, fine. Now, the first combo is strong acid and strong base. Here, nothing is dominating, solution is neutral, so pH will be equal to 7. That's it. We cannot expect any numerical or any, we have no formulas related to this. If any of the system is weak, then we have formulas in that combo. For example, I have strong acid and I have a weak base. In this combo, could you please tell me which is dominating and what will be the nature of the solution?
Acid is dominating, ma'am.
So solution is acidic. And pH is?
Less than 7.
Very good, Kanna. Less than 7. Now, here we have few formulas in this combo. Before getting into the formula, Kanna, what is alpha? What is alpha? Degree of
Dissociation.
Very good. Degree of dissociation. And Ka is nothing but dissociation constant. Similarly, here we're going to use two terms. One is H and another one is KH. This is called degree of dissociation and this is called degree of hydrolysis. Ka is dissociation constant. This is called hydrolysis constant. That's it. So what is the relationship between alpha and K? Alpha is equal to root of Ka by C. Similarly, what will be the formula of H? H is equal to root of KH by C. That's it. C is nothing but we are adding a salt inside water, right? So we'll be dissolving the salt in particular concentration, right, Kana? So that is C. So C is the concentration of salt inside the solution. So here first we have degree of hydrolysis which is equal to KH by C. And we have an expression for KH which is equal to Kw divided by, Kana, what is Kw? Which is ionic product of water, right? Divided by among strong acid and weak base, which is a weaker one, base is weaker one. So for any weak base, we'll be having a dissociation constant, which is Kb. That's it. We're going to substitute the value of KH in this first expression. So H is equal to root of, instead of KH, we're going to substitute Kw divided by Kb into C. That's it. Now pH. We know the solution will be acidic and definitely pH will be less than 7. But we have a formula to calculate the exact pH of the solution, which is half into pKw. Could you please tell me the value of pKw? Value of pKw? What is the value of pKw? This 14, right? Kw value is 10 power minus 14 and pKw is 14, right? And for weak base, the formula is pKw minus pKb minus log C. C is the concentration of the salt. Kb is the dissociation constant of this weak base. And from Kb value, we can calculate pKb. Only these formulas which are related to the second combination. Now, the third combination is weak acid and strong base. Here base is dominating, solution is basic. So pH is greater than 7. So here also H is equal to root of KH by C. Now could you please Guess the formula for KH. KH. KW divided by here, which
Ka.
is very good, Kana, Ka, because here acid is a weaker one. So H is equal to root of Kw divided by Ka into C. And here the formula to calculate pH is half into pKw. Here this is pKa plus log C. Here this is plus, this is also plus. Here this is minus and this is also minus. And the final combo is weak acid and weak base. Here nothing is dominating. A solution will be neutral, but pH will not be exactly 7. They are nearly 7. It can be 6.9, 7.1, somewhere related to 7. Okay. May not be 7 exactly. Here, Kana, here the formula is a little different. See, here we will not have the concentration term at all. So KH is equal to KW divided by, here both the systems are weak. So we have Ka and Kb. So H is equal to root of KW divided by Ka into Kb. We have no concentration term here. So to calculate pH, half into pKw, we should have both pKa and pKb. So plus pKa minus pKb. That's it. Only have to memorize these formulas for hydrolysis of salt. Okay, nothing more than this. Please note it down. I'll give you a problem related to hydrolysis of salt. Shall we discuss a problem, Kana? Okay. pKa of weak acid, pKb of weak base are 3.2 and 3.4 respectively. pH of their salt solution is dash. See, they're asking us to calculate the pH of a salt solution. So it is a very direct question. First of all, we have to find which combination was that. Here they've given you directly the combination is weak acid and weak base, and all the data are given. Please calculate the pH of the solution. pH of the solution. If you want to note the formula down, please let me know. I'll show you the previous slide. Okay, Muthulakshmi's answer is 6.9. How about rest of the students? So here the formula to be used is pH is equal to half into the combos weak acid and weak base. So pKw plus pKa minus pKb. So half into pKw is 14 plus pKa is 3.2 minus pKb is 3.4. If you subtract and add it with 14 and divide it with 2, you'll get the answer as 6.9. That's it. Very good, Muthulakshmi. Fine. Shall we move on to another problem? Okay. Predict if the solution of the following salts are neutral, acidic, or basic. Here they are talking about a salt called NaCl, KBr, NaCN, NH4NO3, NaNO2, and KF. NaCl. Sodium chloride. If you dissolve sodium chloride in water, it will get dissociated into Na plus and Cl minus, water into H plus and OH minus. So this cation and this anion will get combined together. We'll end up with NaOH and HCl. So in this case, this is strong base and this is strong acid. Solution will be neutral. This we have seen already. The next salt they are talking about is KBr. And now we are dissolving KBr in water. Now you guys tell me what base and acid will be obtaining.
KOH plus HBr, ma'am.
That's it. KOH and HBr. Could you please tell me potassium hydroxide is a strong acid, strong base or weak base? Definitely it is a base, but I want to know whether it is a strong or weak. See, it is an hydroxide of a first group element, right? So if OH is combined with group 1 element or group 2 element, then that is considered to be a strong base. Okay, so potassium hydroxide is considered to be a stronger one. So it is strong base. How about HBr? Can you tell me whether HCl is a strong acid or weak acid? HCl is strong acid or weak acid?
Strong acid, ma'am.
Yes, it is strong acid, right? So what it means is HCl's bond can be dissociated and we'll end up with H plus and Cl minus. So here the bond is a weaker bond. That is why hydrogen was liberated as H plus, and that is why it is called as a strong acid. This system can liberate its H plus ion very easily. Right? Now I'm going to give you few more terms. HF, HCl, HBr, and HI. We know HCl is a strong acid. Now we have to know whether HI, HBr, HF are stronger one or weaker one. Okay, listen. For that, we have to decide the strength of this hydrogen-halogen bond. If the bond is weaker, then that can be broken easily, from which H plus can be liberated easily, right? Now we have to know the strength of this hydrogen-halogen bond. We have to know how this hydrogen-halogen bonds are formed. This bond is formed by the overlapping of hydrogen's valency orbital and fluorine's valency orbital, right? What is the valency shell of hydrogen? It is obviously 1. And valency shell of fluorine is 2. Valency shell of hydrogen is 1. Valency shell of chlorine is, I hope you guys know how to find the valency shell of any atom. How to do that? Fluorine atomic number is 9. Electronic configuration is 1s2, 2s2, 2p5. So which is the valency shell? Second shell. That is what I've written here. As far as chlorine is concerned, the valency shell is 3. It is 1 and 4. It is 1 and 5. That's it. So whenever a chemical bond is formed, valency orbital of hydrogen and valency orbital of fluorine are combining together, right? Whenever the orbitals are combining, we have to make sure both the orbitals got equal energy. If equal energy orbitals combine together or overlaps, the bond formed will be a stronger one. At least the energy gap has to be lesser. If the energy gap between the orbitals are large, then overlapping will not be proper. Then the strength of the bond will be weakest. Okay, now tell me which got the strongest bond and which got the weakest bond. All were hydrogen halogen bonds. And I want you to tell me which one is the stronger and which one is the weaker one. For best overlapping, the energy gap shouldn't be there. At least the energy gap should be lesser. Right, Kana? among HF, HCl, HBr, HI, which got the best overlapping and which got the worst overlapping? For best overlapping, the energy gap should be lesser. Yes, Muthalakshmi?
Miss HF is stronger, ma'am, first.
Yes, because the energy gap is very much less. It is the difference of 1, right? In
Yes,
HCl,
ma'am.
the difference is getting increased. HF increasing even more. HI, the worst overlapping, right, Kana? So we know HCl is a strong acid, which means HBr is the weakest bond, right? Comparative to your relative to your HCl, which means this bond can be broken easily. This hydrogen can be liberated as H plus ion very easily compared to your HCl. So now tell me, among HCl and HBr, which is a stronger acid? Which is a stronger one?
HCl, ma'am.
The bond between HCl and HBr is a weaker one, right? So
Yes, ma'am.
HBr bond can be broken easily. If you compare it with HCl, HBr's bond can be broken easily. So HCl itself is a strong acid. HBr is a very stronger one. Okay, HA is a very stronger one, but HF is a weak acid because the bond between hydrogen and fluorine is a very stronger bond and that cannot be broken very easily. Okay, now I have HBr. So it is considered to be strong acid, right? Because hydrogen bromine bond can be broken easily, because of which H plus can be liberated out. Now tell me whether the solution will be acidic or basic or neutral. The solution will be, I'm sorry, it is strong acid here. It is my mistake. It is a strong base. So it is strong base and weak acid. I mean strong base and strong acid. Now the solution is neutral.
Neutral.
That's it. Next, NaCN, sodium cyanide. So Na plus will get combined with OH. So NaOH and HCN. So sodium hydroxide is a strong base, and HCN, this can liberate H plus, but here carbon and hydrogen bond are relatively a stronger bond. So this cannot liberate H plus ion very easily. So it is considered to be weak acid. Now tell me, what will be the nature of the solution? Basic. Next, NH4NO3, which is ammonium nitrate. So what will be the acid and base? What will be the acid and base? Muthalakshmi, your question is, you're asking me whether we can decide using the size of the halogen, right? We can decide, Kanna, the overlapping orbitals size should be similar. See, hydrogen is the smallest one because the valency shell is first shell. Fluorine's shell is second shell, right? Relatively size are similar. But as far as hydrogen iodide is concerned, hydrogen is the smallest one and iodine will be the largest one. Overlapping will not be the rest. So you can see in terms of size or in terms of energy. Anything is fine. Here it is ammonium, NH4 plus will combine with OH. And this is HNO3, which is nitric acid, which is a strong acid. Ammonium hydroxide is a weak base. So which is dominating? Acid is dominating. So solution will be acidic. Next, NaNO2. Could you please tell me what all the acid and base will be obtaining? NaOH plus HNO2. Kanna, HNO2 is different from HNO3. This is nitric acid and this is nitrous acid. Nitrous acid is a weaker one. So nitrous acid is weak acid and sodium hydroxide is a strong base. Could you please tell me the nature of the solution?
Basic, ma'am.
Yes. Finally, potassium fluoride. Could you please tell me the nature of potassium fluoride solution? How
Basic, ma'am.
potassium? Yes, potassium fluoride will get dissociated into potassium hydroxide and hydrogen fluoride. Just now we have seen hydrogen fluoride seems to be a weak acid. Potassium hydroxide is a stronger one. We know that. So in which so basic medium, base is dominating. So solution will be basic. That's it. So we are done with hydrolysis of salt. We have only one concept pending, which is buffer solution, which is related to common ion effect. So in next class, we'll be discussing common ion effect along with the buffer solution. Okay. And definitely we'll be solving a lot of problems from ionic equilibrium, which is a very important and very easy one too. Okay. If you practice it, then it will be very easy. So next class we'll be doing that. And after completing equilibrium, we'll move on to 12th standard. Okay. We'll discuss a very important topics from 12th standard. Fine. After a couple of problems from 12th standard, we'll be starting organic chemistry. Okay, organic chemistry, it is actually a continuous chapter, so we cannot break in between. So we'll discuss few physical chapters first, and we'll get into organic then. If you have any doubt, please let me know. We'll discuss, else we'll close the session. Any doubt? Next class, please revise this entire chapter, Kana. We'll be discussing a lot of questions from both chemical and ionic equilibrium. So please revise, memorize all the formulas required. Okay, fine. Shall we wind up the session? Okay, Kana. Okay. Bye, guys. Bye-bye. Good
Okay, ma'am.
night. Bye, Kana.